we are probably at the end because me and my colleagues will just present afterwards. We are the last two presentations. So probably in the agenda you have seen that we had another title. So I just changed it because probably you already know that we are trying to do the best walking robots in Europe. So you already know us. So I will present some dynamic locomotion in an unknown environment. That is something that we are doing. So just some slides like sponsor about the company that probably you already know, and then some centroidal MPC and footstep planning. Okay. So about the company, you already know there's more or less 20 years that we are working on bipedal robots. But you didn't know that we are sustaining this business thanks to the other business units that you can see here. So we have a very good business in intralogistics, now with the autonomous inventory robot that is called Stopper. Then in mobility with the Tiago, we just presented an Hydra probably in London. You have seen the new Tiago with the serialized actuator and brakes in the arms in order to also enter in the industry, in order to make the pick and place with stable and robust platform. And then for sure social robotics with the ROS for HRI platform that we are pushing open source all around the world. But here we are just focusing on humanoids, and the things that I just present is about the centroidal MPC. So this is more or less the graph that we are doing. So the centroidal stabilizer is modifying locally these references to maintain the balancing under unknown disturbances of the robot. So this is something that has to pass through all this part in order to stabilize the things. So the robot here, the main important part is that we consider the robot like a flexible stuff, and so with this centroidal MPC, we just try to stabilize it using, for sure, the joint state perceived by the sensors. And here is the important thing. So we just, after several tests in the real robots, so here that's just a model, but we did, at the moment we already built 6 platforms of Star Wars robots. So we detected that there's a structural flexibility on these robots. And so using a rigid model, we are not able to do a good compensation. And so we have to compensate this flexibility. And so the idea is just to update the joint position and read the bed encoder according to the torque of the legs in order to make the dynamic walking, and so using better the torque control with this robot. So this is the results. So in the video you can see that we can just use the robots, and here we are using the centroidal MPC, and we can easily transport this kind of data that we are taking with these robots on other platforms, like you can say behind with the other robots. So the idea is, what we would like to have now is to have a robot that you can control with a joystick just in a known environment. So without taking care that the robot can fall down, whatever. So using the perception. So the idea is just to have a stable platform that you can use in order to make a better torque control. And here we have the footstep planning in a known environment. In this video you can see 35 centimeter steps that are executed in 1.2 seconds per steps. So the average velocity of the base is around 0.3, but at the moment what we think, or at least from our understanding, is one of the fastest work that are done with torque control robots in a bipedal robots. And this is just because we were able to compensate the flexibility of the hip that I mentioned before. About the pipeline of the footstep planning, here you can see that we are using the perception with the LiDAR sensor that you can see on the head of the robot. Probably the image is smaller, but you can see the video before. And then we're using the SLIM on automation-based contact planner. And with the centroidal predictive controller that I said, we just calculate the inverse dynamics. And so in this way, we can just have closing the loop, and we can estimate the things in order to make the robot also climbing the stairs or make a better footstep planning. Here there's the results in the video. You see that the robot, what is perceiving in the right side, and this is what the robot is doing. And so we have the elevation map and in green and red the footstep planning, and the robot is able to climb up to 16 centimeter steps. So this development we did in a joint lab that we have with LAS in Toulouse, that is called Dynamograd, with a company, a sister company of Robotics that is there, that is called Towards. Okay, so for French speakers here, I know some of them, you can collaborate with us also in French. And other video, I just went a little bit faster. The other video that I want to just show, okay, it's going here, is the Talos that is able also to replan the footstep and climbing the stairs. This video was, yeah, probably you can recognize, this is the new facility in the LAS, because they changed also the facility. And so when starting the motion, the robot doesn't detect fully the stairs, but it plans only 4 steps. And the replanning online, okay, and adapts to the changing of the elevation map. And see here, you can see in this video, the real things that the robot is doing. So, about the conclusion, the Talos robots we would like to use with a simple joystick, so a gamepad, and this is what we are doing, and as to be able to perceive and replan online the path. So this is what we achieved, but there's a lot of things that have to be done yet. And so we would like, for example, to improve the estimator, introducing also the SLAM, and also improve the post-processing of the elevation map that you have seen. So at the moment, we are just doing this. Then plan the collision-free footstep trajectory in a more complex environment, and use a global path planner to avoid local minimal during the footstep plan. So. Thanks for your attention, but I just let the word to my colleague Luca that will present the Talos, the Kangaroo platform, and then we can just make the question at the end, because probably you are tired, so you want to go to our team. Luca.
Thank you. So I'm Luca McConney from Robotics. This is one of the latest platforms that we have developed. It's Kangaroo. We started this with a motivation that we want to have robot more agile, and we were, as you have seen before, the Talos robot is a very heavy, big guy, 100 kilograms, and we were facing problems with the robustness of the platform, especially the speed of the motion that we can get on Talos is not so fast as we would like. So we started looking at what we can do for improving the performance of our robot, and especially taking inspiration by parkour or the amazing work that has been done by Boston Dynamics. So we wanted to change the paradigm for designing a new biped robot. And actuation is a bottleneck, transmission it's a pain in the ass, and you need to have a robot that is robust. You need to brake and you need to fix it quickly. So we started thinking, can we build a robot that can jump? And by some simple physics, we started thinking about what's the minimum viable system that can jump using as less as possible actuators. And we started looking at what is outside. Now this list can be extended with the new entries by Figure, 1X, Tesla and Actronic. Now it's the challenge to the human seems to be very active. And we compared the kinematics and actuation system of different robots. And what we were looking for is something a little bit more, let's say, novel, and that was efficient enough so that control can be done easily. And we came out with this new system that we started calling leg length actuation system, so which we only one actuator and two closed kinematic chains, we can actually contract and extend the leg in almost a vertical line, and that is quite, let's say, convenient because, for instance, for standing up from squat position, for stepping on spot, you only need one actuator. And we built this system, and we did a very stress test on this system. Actually, last week in London, we made more than 1,000 jumps during the conference with this system with 15 kilograms on top. And this system is using one single actuator with a ball screw. We have a force sensor that we developed in-house that is used for measuring the actuator force. And the transmission is non-linear because of the closed kinematic chain, and the system is quite resilient to impact. That is one, and quite transparent, thanks to, let's say, the selection of component that we did. The ball screw is off-the-shelf component, and the key here was to size the kinematic chain in such a way that you can shape the transmission in a convenient way. So having enough torque when you need it and enough speed when you need it. Also, with similar ideas, we started figuring out how to design a hip system using, again, linear actuators. This is the system that we use for the roll and pitch joint of the hip. It's two linear actuators combined in a differential configuration. And also this demonstrated to be quite transparent, and we can do inverse dynamics, and we can do gravity compensation with the integrated load cell. And then we built the lower body of this robot, and now it's, let's say, already validated and tested, 12 degrees of freedom, everything is concentrated, all the actuators are concentrated in the base of the system, and we developed custom electronics for this, and this is something that we are trying to exploit as much as possible in terms of extreme or high dynamic motion. The system is complex because of the choice that we did about linear actuators and move them in the base. We have a full system that is composed of 76 degrees of freedom, and that is challenging in terms of modeling, in terms of simulation, in terms of control. Everything is non-linear, so it's something not as easy to control, especially with, let's say, traditional off-the-shelf libraries for physics or for inverse dynamics, inverse kinematics. But the benefit in terms of control or template modeling is evident. If we compare the legs of Talos with the legs of Kangaroo, you can see that we reduced the weight of almost 50%, and especially the center of mass of the leg system is way up in the kinematic chain, meaning that it's easier to control the robot with a template model, with a linear inverted pendulum reduced system, and they are ordered to make it's smaller than with other robot as Talos, and also in terms of moving inertia, respect the hip joint, it's 1/3 smaller the inertia, the principal around the principal axis, and also this at the end translates in lower energy that you need to dissipate during the impacts. So the robot is going to resist better dynamic impacts. Some videos about the workspace exploration of the robot, balancing on the 2 feet, the compliance control with the whole body control stack that we have, and some first experiment that we did with the robot jumping. We made up to 20 centimeter jumps, more or less, with the full, let's say, with this lower body bipedal system, and it's still the limitation mostly is on the control stack, because for doing this we were using our whole body controller, using the ground reaction forces that we estimated using some trajectory optimization and simulation. So there is a little of study that we are doing in the control pipeline. We are taking inspiration from MIT guys that have done a great job with the mini cheetah robot. We are looking at how to build up the chain of MPC controllers and tuning the parameters and estimating the model for making it more robust. And these some more, let's say, recent results. So the robot can balance blindly on a moving platform, can walk using still, let's say, small steps and not very fast walking, but the robot is quite stable. and we are quite satisfied with the this is for us also is a great achievement because it's the first time that we managed to have a robot walking using our own custom electronics, because in the past we were using commercial electronics like Elmo in Kenya especially for the legs, because of the high bandwidth that we were needing for controlling the motors. And in this case, everything has been built in-house, so we can control a lot more how the firmware is controlling the motor current, the online torque control at joint level and sensing. And this is a little bit the roadmap that we have, so to distribute the low-level control as much as possible, to simplify the load, the computational load on the central computer, so that we can use more advanced control algorithms as MPC or trajectory optimization. Conclusion, so Kangaroo is a new bipedal robot with, let's say, novel leg architecture and actuation. We believe that because of the complexity and the choice that we did at design level, it should be easier to use Kangaroo with template models, so simplifying the model, even if the hardware is more complicated. There is the complication of handling non-linear transmission, and this can be done at control level using optimization, quadratic programming, or even we are figuring out the, let's say, the geometrical function for directly having the equation of the transmission. And then we want to demonstrate the benefit of this novel architecture with very, let's say, dynamic behaviors. In the future, what we are doing, we already started selling the lower body of Kangaroo as a research platform. We offer, let's say, the typical services that we offer with all other products that we have already commercialized in the last years. So there is this, all this cross ecosystem integration, simulation, plus already built-in demonstration like walking, whole body control, inverse kinematics, inverse dynamic library that we provide out of the box. We are going to do more experiments and more demo for sure to push the robot to the limits. And also we have been starting thinking about upper body for the robot, because at the end we want to have a full-size humanoid. And we are going to exploit probably part of the result that we recently announced about the new Tiago robot with series elastic arms that we showcased at the NICA a few days ago. And a little bit of hint about what's next that we are going to try to the robot. So what, as I told you before, about all the pipeline, about robot trajectory optimization in cascade with modern predictive controllers and whole body inverse dynamics, so that we can, let's say, achieve this dynamic motion jumps, running, and fast step recovery in complex situation. Thank you, everybody.
I would have a question. So the jumping looked quite nice, and in the conclusion you said that this will enable dynamic motion and this impact zoom or something. Could you, because when we're looking at this jump at touchdown,
the bouncing.
Yeah, so it's bouncing. So are you aiming for running, or because then I would be, I don't know if you would imagine. So it doesn't look that much. It looks quite difficult with this motion, I guess.
Yeah, I mean, the robot has no flexibility, everything is rigid, so any compliance should be controlled actively using force control or control agenda. So in this case, there is this limitation that this experiment was using only whole body control, so there is no preview horizon. We were trying to track instantaneously the ground reaction forces. Yeah. So I think that improving the way we can track not only instantaneously at decided ground reaction force or at COL trajectory should allow for basically even trying to dissipate the energy during the impact all over the robot. Because one of the reasons is you have an instantaneous impact here, and the reaction time of the controller system at the end is limited. So you have this bouncing if you are not probably using the right reference trajectories.
So at which dynamic motions are you aiming for then?
With jumping, running, or even very fast step for push recovery. No, that's the typical
So Luca, just a question on the fly. So what prohibits you to touch down with the compliance?
No, just no.
Can you repeat the question?
Sorry?
Repeat the question, please.
What?
What prohibits you to land with the compliant behavior?
No.
As a controller.
In this case,
Can you repeat the question, please?
what forbids us to use more compliant behavior during the landing? In this case, being only active compliant control, it's just a matter of the parameters or the bandwidth that we have in the force control. That is the only limitation. Yeah, that was first.
Oh, thank you. Okay, so I don't mean to compare apples to oranges, but it's a quick conceptual question. So a lot of these sort of anthropomorphic bipeds that I've seen, like cows and kangaroo, they have like a pretty large knee flexion. And so if I were to compare it to human gait, it's kind of like a crouch gait type looking thing. Why is that seen in so many different bipeds that people are developing, this large knee extension or flexion?
On Talos, I mean, the robot can be complete with any complete stretch. It's more a problem of the inverse kinematic that we want to stay away from the singularity. It's just a limitation of the algorithm. On this case, it's more of, let's say, mechatronic limitation, meaning that you want to have you don't want to be close to the ball screw that we have in the femur. If you stretch completely the leg, it's going to be in a singularity, so you cannot get out of that singularity anymore mechanically.
So you're just trying to have room in joint space to handle maybe disturbances or okay, thank you.
That's one reason. The other one is that people like this linear inverted pendulum model. and that model depends on keeping the height constant. And if you have the leg straight, you lose control over it. We can't have a height constant for the leg straight because of the maximum and the masses over the leg. There's two bad reasons.
So the slip template is a big part of it.
The slip, not the slip, it's the lip.
Oh, sorry, yes.
The lip is one, and then they don't like their programming goes sour because they don't know how to deal with singularities. So rather than learning how to deal with them, they just make the robot walk with no legs.
Thank you. Thank you both.
Do you agree with what I said?
Yeah, it's much correct.
Maybe I missed it. Looks like the ankle is actuated. I was just wondering.
Yeah, it's actuated.
Where's the actuation? What's the transmission kind of thing?
The ankle actuators are actually placed on top of the here. You see here?
Are you pointing just
Okay.
Yeah.
So these are the actuators of the ankle, and actually these bars are propagating the motion to the joints. That also was actually something that we discussed quite deeply in the design phase, because a simple solution could have been to put here in actuators. Moving those actuators there has another benefit, that when you contract the leg in place, actually without activating the ankle motors, you keep the orientation of the foot parallel to the ground. So again, for standing, for squatting, or for just stepping in place, one only actuator per leg is activated. That is the one that we discussed before about the called leg length actuator.
With all those transmissions, how bad is backlash, elasticity, all that, all those goodies?
It's a lot of iteration in it, especially for not everything can be simulated, and especially also a lot of attention should be put on the selection of the ball screw, on the backlash of the ball screw, and also on the bearing, on the spherical bearing that you use, and how you integrate them in the structure. You have many parameters, many more parameters mechanically than from a traditional rotary joint with planetary gears. So it's a lot of trial and errors.
The trial and error in the getting the play out of the joints or in the control system?
It's a little bit of everything. In the design phase, in the selection of the components, in the building phase, because also as you have a lot of parallel system, minimum differences between the length of the links can introduce internal forces that can create backlash or not ideal.
Okay, but when you're all done, it's built, it
Yeah.
has some backlash, it has some friction,
Yeah.
the motor's not ideal. How do you contend with that?
I mean, one complicated part of this is that during the calibration phase, it's much more complicated than a typical serial system. Yeah, because you need basically on this system, calibration is also affecting the way you map actuators to joints. While normally it's a problem that is not so important when you have a serial program. Because we need Jacobian everywhere here, only for controlling the robot.
So do you actively do anything in controls to deal with backlash, elasticity, and linkages?
No.
Or you just
We try to reduce it as much as possible during the building of the prototype, and then we are trying to implement a lot of, let's say, calibration routine, so that from time to time you can recalibrate the system for absorbing or at least mitigating the effect of backlash introduced with the use. Just from the...
How hard do you think it will be? You're saying building, you have to be very careful. Will it be harder than making in serial production?
That was also a bet that we discussed if to take or not. The good part of this robot that we have only two types of actuators. So there is the big one, that is the one in the femur, and then all the other actuators are all the same. So what we are doing is we are building tooling jigs for actually calibrating each individual actuator before assembling it on the robot, so that we can do offset calibration, estimating the offset of the sensors, and do proper modeling of each actuator before integrating in the system.
So you explained that there's the big actuator, you talked about the hip, there's two there, you talked about the ankle. So there's 6 per leg. What are the other degrees of freedom?
Yeah. So this is the hip yaw actuator.
Okay. So, yeah, okay.
Then on the front, 2 on each side, we have the 2 parallel actuators for the pitch and roll. These are actually 4 actuators that goes in 1, 2, 3, and 4 that are on the back part of the femur that are used for actuating the ankle. And then we have the big one that is the one here. It's basically the head of the femur. That is the one actuating the ball screw hidden inside the femur.
How do you keep the ankle actuator from producing torque about the hip and the knee?
Sorry, can you repeat?
How do you keep the ankle actuator from producing torque about the hip and the knee? Or does it produce torque?
No, it doesn't produce, because this is a completely passive joint here. So thanks to the closed kinematic chain here, you have 2 4-bar linkages. So when you contract the foot, the actuators here are immuted. You only change basically the angle of these 2 parallel chains.
I don't think you answered his question. Does the ankle have a degree of freedom?
Yes, 2 degrees of freedom. Roll and pitch.
Do you understand?
Well, the knee is a passive outcome of it's a kinematically constrained thing. So
Yeah.
you don't care if you produce torque about it, it's kinematically constrained.
Exactly. Yeah. Francisco?
You mentioned you have like custom sensors.
Yeah.
Where are they? And are you measuring
Are
them
integrated into the actuators.
into the actor in each of them? Yeah. And is it like one load cell? Or?
One axial load cell per actuator.
Does that cause actually the issue instead of having like some sensors closer to the joints?
Yeah.
Because once again, like backlash, all
Yeah,
that's
I
going
mean,
to be.
control guys would like to have a sensor everywhere. Yeah. If you have 76 degrees of freedom, they would like to have 76 encoders. Yeah.
All the doubles.
So, can you talk a little bit more about the 64
Yeah.
unactuated degrees of freedom?
Yeah. So this is what we have 2 models. This is a simplified model that actually we are using now for all the demonstration demo that you have seen. We are using this one, in which the only passive DOF that we are modeling are those of the leg length. Again, the leg length actuator can be thought about like a virtual prismatic joint that is connecting the hip to the ankle. But in order to take into account the mass and inertia of the femur and